recording. So let's start then. So first of all, everyone, welcome to our third Energy Sources webinar episode brought to you by Newcastle University Centre for Energy. Thank you very much for everyone who's attending today, especially our two speakers. So today our theme is hydrogen energy, and we will be listening to very interesting talks by Dr. Eni Oko from our own Newcastle University and Anna Peecock from the University of Aberdeen. They will give talks about their research projects and will be available to reply to any questions from the audience during our panel session that will start after all the two presentations have been delivered. The webinar today aims to promote a great discussion around hydrogen energy and promote wonderful research and cutting edge techniques like the ones that they are using in their work. So with no further ado, let's introduce our first speaker for the day. So our first speaker is Dr. Eni Oko, Process and Energy Systems Engineer and Senior Lecturer and Associate Professor in Chemical Engineering at Newcastle University. Previously, Dr. Oko was awarded his doctorate degree in Process and Energy Systems Engineering by the University of Hull, where he also worked as a postdoc researcher and lecturer in chemical engineering from 2019 to 2022. Since then, Dr. Oko has established himself as a leading researcher in his field, counting with industrial and academic collaborators in the UK, China, Norway, Belgium, South Africa, and Nigeria. With an impactful record of publications and academic prizes, including the Institute of Mechanical Engineering Ludwig Mond Prize 2014, Dr. Oko has secured over 900K in research funding from different organizations and had one of his publications represent a great part of a 2020 report from the UK Department for Business, Energy and Industrial Strategy. So, Dr. Oko, thank you very much for accepting our invitation today. And whenever you're ready to start and share your presentation, we are ready to listen. Thank you.
Thank you. Good afternoon, everyone. A presentation. I'm sorry, I'm not sharing yet. So my presentation is on ammonia tracking system. So my presentation today is on ammonia tracking system. I will talk you through a bit of the things that we've been doing in this area. In this area, I have little bits of grant that I have done. Royal Society, which is ongoing. So the Royal Society project, working with some guys from University of Pretoria in South Africa, and we're using a computational method to try to formulate new catalyst designs for ammonia tracking. Then we'll have a project that just ended, was funded by BASE. And in this project, we have ammonia tracking system integrated with an ammonia production system. So trying to have a plasma-driven ammonia production system that can produce ammonia directly and then go through ammonia tracking to produce hydrogen. Then the last one was from Network H2, it's part of EPSRC project. And this particular one, we're looking at onboard ammonia tracking. In other words, having an ammonia tracking system in a transportation system. For example, a civil airline. Right, so my presentation, we have a quick look at the background. I know that will probably be trivial for many persons here, but you just bear with me. I think it helps to build the story of a story I'm about to tell you. And then I will talk about hydrogen storage and ammonia as a hydrogen carrier, look at a bit on the R&D landscape, the greatest news, out of this area in the past couple of years. And then before I can now talk about the model development and the results. I'm sorry if you are here solely for the model development, it's coming very last. Right, so in terms of background, net zero targets in the UK and many countries And of course, fuel switch is a key strategy for delivering net zero target, especially in hard-to-abate sectors. This will include the transportation sector, heavy industries, and in the case of UK and other cold nations, this will also include domestic heating. Hydrogen is recognized as a key fuel, so if we are going to do fuel switch, it has to be hydrogen for most cases. And the UK already have a hydrogen strategy in place, which is expected to develop, to help build the momentum to scale green and blue hydrogen system production, right? The interest on hydrogen is essentially because it has significant amount of energy in terms of gravimetric energy density compared to many fuel. It is not as such when you look at the volumetric energy density, and the implication of that would then be that you will require higher storage volume if you were to store hydrogen or transport hydrogen. You require higher storage volume than you would do with diesel, gasoline, etc. Right. So why hydrogen is praised to heavens to have this potential of helping us achieve net zero. The key issues are in the area of transporting and storing hydrogen. There are reports that confirm that hydrogen has greater explosion risk, up to 4.5. The other point is that hydrogen is commonly transported as compressed gas, and as compressed gas, the pressure could be as high as 700 bar, which brings in additional risk. Okay, and of course, that is also quite expensive to achieve. The other point is the low storage density of around 40 grams per liter at 700 bar. Of course, the other point is that there is a risk of hydrogen embrittlement. This then means that there are special materials are required for producing hydrogen storage tanks. Carbon fiber materials, which is commonly proposed and used, is very expensive and it's very energy intensive to manufacture. Those are some very key issues with compressed hydrogen storage. Then in liquid phase, you are going to be transporting and storing hydrogen at incredibly low temperature of minus 253 degrees C, which brings its own additional risk. And of course, it's expensive to operate at this type of condition. The storage facility, because of that, is highly complicated. And in the case of the transportation sector, there's also going to be longer refueling time. I bet the good side being that it has relatively higher storage density compared to compressed hydrogen. But we can have ammonia carrier rather than hydrogen. In other words, ammonia acting as a carrier for hydrogen. And at the point of use, this ammonia can then be chemically broken apart to extract your hydrogen. If this solution is adopted, it has higher storage, far higher storage density compared to transporting or storing hydrogen as itself. And the other good side is that the ammonia handling is very well established, and this can be done at relatively mild conditions, such as 10 bar and 25 degrees C. So, and so this is ammonia transport, long-term transport, large-scale storage are all operations that are well established in the industry. Right? So, so on that basis that we are certain that hydrogen has to be transported by some sort of carrier and not as itself, especially at very large scale. Right, so there are different propositions regarding how hydrogen can be transported and, stored at commercial scale. And each of them have their own benefits and advantages. The absorption technique have low energy requirement for recovering your hydrogen. However, the operating temperature is still very low. And then the hydrogen carrying capacity is also low. The other one is chemical storage using unsaturated liquid compounds. Again, low hydrogen storage capacity. The reactor designs are a lot more complicated, and they require very high energy requirements to extract the hydrogen. And generally, the technology readiness level is still very low. Then we have other storage compounds, and this is where ammonia, metal hydrides, and methanol comes in. Ammonia brings a lot of advantages. The storage capacity is relatively higher. I'm not seeing, sorry. Oh. Okay, and it can be stored at mild conditions. Then, of course, this is just a chart that shows you where ammonia is compared to lots of chemical compounds that can be used for ammonia storage in terms of the energy density. And you can see that ammonia is far ahead of most of them, right? Then this shows the energy requirement for liberating hydrogen from ammonia. And of course, other popular hydrogen carriers. And you can again see that the energy requirement for liberating hydrogen from ammonia compared to a lot of them is actually relatively lower. Ammonia is considered as having the potential to form an important part of hydrogen supply network in the UK and in many countries. And here is an illustration of how this looks. Different routes have been proposed, either having a centralized ammonia tracking system closer to the end users, or having ammonia tracking system at every end user location. There is a BIS report that was commissioned a few years ago, where they tried to look at the the cost of each of these solutions, and which showed greatly that the decentralized routes, in other words, having ammonia tracking system at different end user location, is actually going to be relatively cheaper compared to having a centralized ammonia tracking network. The other point is that there is also potential for having tracking ammonia on board. So like marine system and heavy transport systems. A company in the US called Starfire has done lots of work in this area. And this is essentially how it looks like, where you, instead of storing hydrogen, you can be storing ammonia on board. And then at the point of use, it can be pumped through a tracking system. Essentially, this particular setup here is looking at partially tracking the ammonia, so that what we have going into the engine would then be a mix of partially tracked ammonia and, of course, fresh ammonia. They've done tests that includes cracking around 30% of the ammonia and then mixing that with a completely 70% ammonia. So there are different reactor designs. The second design is actually separating the nitrogen, right? Whereas the first design is actually mixing everything that is being cracked as it goes into the engine. This second design separates the nitrogen and takes nitrogen out, and it shows that this is a lot more efficient. There are quite a bit of activities that has been ongoing in the past couple of years in this area. CIRO in Australia have done some demonstration of ammonia to hydrogen pilot system for fueling for fuel cell vehicles. And then, of course, there's a TransHyd project in Germany, where they are looking to build this massive hydrogen transportation infrastructure, and ammonia is expected to play a significant role in the TransHyd network. A company called Amoref is working on the ammonia tracking system. Then in the UK, the UK Science and Technology Facilities Council, working with Reaction Engine, has come up with a gas turbine concept for aircraft engine concept that we have that will include an ammonia tracking system. Okay, In the US, NASA is funding a very similar project with which is being led by University of Central Florida. In the UK last year has awarded a grant for the Teasley project, which again involves some ammonia tracking and is expected to deliver around 200 kg per day hydrogen to a fueling station. Right. So the main point now is in the ammonia tracking is actually the reactor. It's while everybody has been talking about their concept in terms of the key challenge here is in the ammonia is on the reactor, right? The reaction is highly endothermic. Okay, the energy intensity is very high, and the other problem is that it's equilibrium limited, and this limits the amount of ammonia conversion. We did a tubular reactor model at the start of our project. This is a part of the results that we got from our tubular reactor model. But what this shows is like you can see that there is a limitation on the amount of conversion that you can achieve with a tubular reactor setting. Then, of course, there are different technologies, for cracking. Either the electrochemical decomposition, which is extremely new in the setting, and the thermal catalytic cracking. What we are looking at in our project is based on thermal catalytic cracking for a number of reasons. It's very much more established. The key challenge is essentially in the reactor, the catalyst development challenge issues, okay? Then this is the two types of reactors, essentially. Either having tubular reactors, and these tubular reactors, the product then goes through some separation where you separate the hydrogen from nitrogen and, of course, any unused ammonia. Why this is okay for many cases, there is a very high potential of low conversion because, as I've mentioned, because of the equilibrium limitation for this particular reaction. The other type of reactor is catalytic membrane reactor, which is like process intensified. You have a catalyst somewhere at the center, and you have a membrane separator layer. So essentially, as the hydrogen is being formed, it's taken away, and that kind of drives the reaction to remain in the forward direction. And by so doing, we can achieve very high conversion. We can also achieve very high hydrogen recovery. And the other important point is that we can also have a reactor that is smaller in size compared to the tubular reactor setting. For our model, we are working on essentially on the catalytic membrane reactor. But as I say, at the start of our project, we have also looked at tubular reactor designs. So we have, this is a simplified format of what the membrane reactor that we have worked on, and quite a complicated kinetics because it also tries to include the kinetics of the membrane itself. We've modeled this as a custom model because this type of reactor models are hardly available in commercial simulators. And we have created a custom model from scratch in a software called the ASEAN. And we have tried to look at different catalysts. But what I'm going to show you here is just for the lithium amide catalyst using a palladium-based membrane. So we have a number of analysis that we've done with our model, and this was looking at different membranes with different permeability coefficients, and we could see that, of course, if you have the ones with higher permeability coefficient, delivered better recovery for hydrogen. And we have also looked at specific points in the reactor and looked at increasing the temperature, operating temperature, starting from around 470 degrees all the way to around 650 degrees. What we found is that higher temperature is actually was not good for the membrane, because as we have higher temperature, the hydrogen permeability declined, although it declined by just a little amount. The other point was looking at the pressure. Okay, so as expected, higher pressure drives up the amount of hydrogen, that can be recovered through the membranes. Another work that we had done, which is part of a different project, was looking at, because most of the studies and companies that are looking at onboard applications seem to focus only on the reactor, so to speak. So part of the things we have done in one of our projects was to look at the space that you need to store ammonia, on board. And in this particular case study, this was gladly supported by partners from Cranfield University Aerospace Center. And we've done some comparison with standard jet fuel, looking at an A380 massive aircraft, and just placing them side by side in terms of the energy requirement and the amount of, if this was to flip around and you use ammonia, how much storage space that you will need to store this ammonia. And our analysis just showed that ammonia compared to jet fuel in terms of volume ratio, that you will have a volume requirement of 2.65 for ammonia, greater than that of the jet A fuel. So worked out the in terms of volume, and it is a lot of volumetric requirement for ammonia storage. And then because their liquid ammonia is expected to be stored in the form of at a high pressure of 10 bar, the standard designs of having storage tanks, standard design for aircraft. So if you look at this aircraft sign, you will see the pink color here is where the fuels are usually stored in standard aircraft. But this, because this storage is atmospheric, so to speak, ambient, is stored at ambient condition. In the case of ammonia, it's not going to be stored at ambient conditions. And what we have learned from our partners in aerospace is that at 10 bar, it's impossible to store at the wings. And this is part of the things that we found out. And then they've proposed that if this sort of arrangement goes ahead, they're going to have like ammonia storage tanks, within the body of the aircraft, rather than the wings. And the volume that is required is huge. All right. So in summary, we have developed CMR reactors and tubular reactors for ammonia cracking in Aspen custom modeler. The tubular reactors, as we found, is greatly hampered by strong equilibrium limitation of the ammonia tracking system. The catalytic membranes have showed better conversion and hydrogen recovery. And then in terms of onboard storage capacity, a sort of new bottom-up airliner design is going to be required, and not retrofitting existing design. And just some shout outs to all the organizations that have kindly funded our work. The Network H2, which is part of EPSRC, the Royal Society, the BASE, and of course, all the various organizations that I have had the privilege of working with. Sheffield University, University of Hull, CPI, Robert Gordon University, Lucidion, University of Pretoria, and Cranfield University Aerospace, and of course, all my research assistants that have worked with me. Thank you.
All right. Well, thank you very much, Dr. Oko, for your talk and for sharing your amazing work with us. We had some questions in the audience, but just reminding everyone, we're going to answer the questions after the second presentation during our panel. So keep with us. So now we'll be hearing from our second speaker. So our second speaker is Anna, second-year PhD student from the University of Aberdeen, working under the supervision of Dr. Afonso Martinez Felipe, from the University of Aberdeen, and Professor Russo Makina from the Swiss Federal Institute of Technology in Zurich, the ETH Zurich. Anna previously obtained her BSc in Natural Sciences from Durham University and her Master's in GeoEnergy from the University of Edinburgh. And Anna is now carrying out very interesting research focused on incorporating hydrogen into offshore energy system integration modeling. Anna's trajectory also includes a recent first author publication in the journal Geological Society about mapping hydrogen storage capacities of UK offshore hydrocarbon fields and exploring potential synergies with offshore wind. Anna has helped facilitate the Scottish Schools Hydrogen Challenge, a national outreach project that inspires school students to design and build hydrogen fuel cells powered cars. And she is also part of the committee of the recently launched Women in Hydrogen Scotland professional network. So Anna, thank you very much for participating in our webinar today. And whenever you want to start, the stage is yours.
Thank you very much. Let me just share my screen. Sorry, I'm going to go. Oh, perfect. Thanks.
Oh, sorry, guys.
Okay, hopefully you can see my presentation now.
Yes.
Perfect. Right, let me just make sure I can. Right, okay. Hi everyone, and thank you very much, Anna, for that introduction. As you say, my name is Anna Peecock. I'm currently in my second year of my PhD at the University of Aberdeen, and I'm looking at modelling offshore energy system integration, specifically in the UK North Sea. Right now, this isn't clicking through. Okay, so I firstly just wanted to quickly introduce my background. As you said, you've kind of already covered it, but I started doing my undergrad at Durham, predominantly focusing on chemistry, which I did really enjoy, but quite early on, I realized I was drew to the kind of the practical applications rather than to the theory itself. So I took a step back from academia. I went and worked for an energy company for a year, but I quickly realized again that I was like, I really enjoyed learning, and it was one of those classic things I was really keen to do more. So I went back in and signed up for my master's in GeoEnergy at Edinburgh, because I'd realized that like the energy sector was definitely somewhere I wanted to stay. And from that, I was then able to apply and luckily get the funding for the PhD in Aberdeen, where I currently am. So throughout the presentation, I thought I'll give you a bit of context and background to my project itself. And then I'm going to delve deeper into the hydrogen related parts. As you'll see, I'm kind of looking broadly at offshore energy system integration, but two of the hydrogen specific sections I think will probably be more relevant to this forum. We're looking at mapping hydrogen storage capacities of UK gas fields and also analysing limits of electrolysis performance. So just to give you a bit of context. So as our energy sector becomes more complex and has a greater degree of diversification and new technologies, it's really important that the models we use to describe our energy systems are able to reflect this. So as, for example, power, heat, transport, domestic and industry, energy storage, they're becoming far more interconnected. And so if the models that influence our policies can't accommodate this increasing degree of interdependency, then we risk like producing inaccurate forecasts and potentially leading to consequences like missing decarbonisation targets. So this is particularly evident when it comes to offshore energy system modelling. So the current models often resort to aggregating significant amounts of data. And in an area like the North Sea, which is at the same time home to hundreds of energy assets and is a key region for the UK and its other bordering countries' energy transitions, it means that we're unable to analyse the potential development pathways and evaluate kind of the pros and cons of different strategies if we can't look at this in enough detail. So that's kind of the challenge that I am trying to address within my PhD in collaboration with my supervisors and some other people along the way I've had the opportunity to work with, both in academia and industry. So through a combination of model development and experimental research, my aim is to evaluate potential synergies between the UK oil and gas sectors and the offshore wind sector, to explore both economic and environmental benefits that we can be achieved through kind of the co-exploitation of the two of them. So I'm developing an energy system model to explore and optimize future energy scenarios for the UK, hopefully with the capacity to guide long-term energy transition policy decisions. And basically the main output will be a roadmap for UK North Sea decarbonisation. So we'll be looking at individual assets on a really kind of high resolution basis. So we can produce a roadmap, so potentially for which oil and gas fields or platforms can be decommissioned first, so as to ensure energy security, but benefit us throughout our energy transition. But as I said, the modelling side of it is both very technical and probably not as relevant here. So I thought if I talk a bit about some of the work we've done for looking at hydrogen. So firstly, thank you to Dr. Oko for introducing this. It means I don't need to cover as much as the background, as I'm sure you're already familiar with it already. So we approached this study from two angles. One, quantifying the amount of hydrogen that we actually need to satisfy the UK domestic heating demand. So in both the case of a 100% conversion to hydrogen, which I would argue kind of on current timescales is less likely, but also the 20% blending scenario that appeared in our energy white paper from Bayes, and also in kind of our national decarbonisation strategy. So we're looking at heating on the one side, and then we also wanted to determine the hydrogen storage capacities of depleted gas reservoirs in this context. So do our gas reservoirs, which are probably our largest storage, geological storage option, do they provide the storage capacity that we would need for such a large hydrogen requirement? So as I'm sure you're aware, just for context on heating, in the UK we import a lot of our natural gas, both as natural gas and LNG. And in theory, when we're looking at the gas, we buy it when it's cheap, inject it into a storage reservoir, which we know is adequately sealing because we've stored gas, or gas has been stored there for millions of years, and then we produce it as and when it's needed. But in contrast to electricity, where our demand fluctuates on daily, hourly timescales, the demand for heating, which is largely met by natural gas, fluctuates massively over the course of the year, which is what makes it such a challenging sector to decarbonise. And we therefore need a significant amount of energy storage to ensure energy security, as we found out over the last 12-24 months. Geological storage, as I mentioned, offers energy storage on seasonal timescales. So we focus specifically on depleted gas fields, where we have the historical evidence of effective storage. And this could therefore serve as a vital tool for decarbonising the UK's heating sector, which on its own accounts for more than 20% of the UK's total carbon emissions. So if we can tackle this, we're well on our way to meeting our net zero targets, but also I go the other way and say I think we're going to struggle to meet our net zero targets without tackling this.
Anna, I'm sorry to interrupt you, but I think your slides they're frozen at some point during the presentation. So
I'm just about to move it on.
Oh, so okay. Maybe not then. Okay.
No, don't worry.
Cool.
Just
great.
Talking about the background here, but thank you.
Right.
So yeah, just to talk about our study, we specifically focused on the potential storage capacity for hydrogen within our UK offshore fields. And then we were looking at identifying the greatest potential for coupling with offshore wind. The idea being that green hydrogen can be generated from offshore renewable electricity and stored and then transported via existing natural gas infrastructure as required. So moving on, using accessible field data, we calculated the potential energy storage capacity of gas reservoirs on the UK continental shelf. So here you can see an excerpt from a GIS resource we've created, showcasing both the results of this study, and I've expanded it to include CO2 storage capacities too, as obviously there'll be a competing interest for both hydrogen storage and CCUS. So I also, within the study, it's worth noting, chose to include operational fields as well, as depleted reservoirs, as are usually kind of considered in this kind of context, as the increasing pressure to reduce fossil fuel production could lead, hopefully, to some of these fields facing decommissioning sooner than expected. So this study built on the work of a colleague at the University of Edinburgh from when I did my master's there, and together we developed a database of 96 hydrocarbon fields in the UK continental shelf, and these have a cumulative hydrogen storage capacity of just under 3,500 terawatt hours. So by comparing that with our seasonal heating demands, we know that the capacity exceeds the amount of hydrogen we need for a 100% hydrogen grid by more than 25 times. So we are not going to we're not going to run out of storage, seasonal storage capacity, which is obviously a good thing. So the next stage, as I said, was to explore the combination of green hydrogen produced using surplus electricity generated by offshore wind with the storage in depleted fields. So here you can see the 43 of the 121 existing offshore wind projects that are either in their early planning or pre-development phases. Those where the incorporation of hydrogen is far more realistic and attainable. We then, in consultation with a team of industry experts from a range of different backgrounds and specialisms, developed a weighted criteria framework based on which we could rank the fields basically in terms of suitability for coupling. And you can see the fields in relation to the offshore wind farms on the map on the right, and then the criteria that we applied weightings to. So this was our final output, and it highlights the 10 highest ranking fields that are identified as optimal for coupling, with offshore wind as part of our green hydrogen generation and storage system. Now, it wasn't specified whether the hydrogen would be produced onshore or offshore, so we left that open to our industry experts as to how they weighted the different things. So that was considered in this. And then the next phase of this research is to determine the most suitable fields for storage based on intrinsic parameters, so reservoir conditions, cushion gas requirements, and then compare these results to a cost analysis for fixed and floating offshore wind on the UK continental shelf. So basically to see which fields that we consider optimal for developing its storage sites are within close proximity to an economically attractive area for wind developers. So almost working in reverse to the way we did it, where we prioritized existing wind developments. So here you can see, again, just the key conclusions from our work, the total storage capacity exceeding 3,454 terawatt hours. Most of the suitable sites for coupling based on starting with pre-existing offshore wind were in the Southern North Sea and East Irish Sea, but I think this would change if we were going from the other way. I think we'd see far more fields in kind of the North of Scotland region, which have a great wind potential and kind of be shown to be optimal. And the methodology we've developed can be kind of applied to any region. We're looking at a very high level, obviously site-specific studies would be needed to assess the technical feasibility of storage within different geologies, particularly with regard to microbial reactions. And then obviously the other assumption we've made is the feasibility of repurposing, which there's lots of work going into at the moment. So we can definitely build on this kind of in the future. And if you want to read more about it, this is the DOI for the paper we published. So taking a step back from that, that study will provide a modelling input that we'll then use when considering repurposing options for our North Sea assets. But the other side of the hydrogen-related work we're doing is looking at analysing the limits of electrolyser performance. So for both offshore and coastal green hydrogen production, seawater presents kind of an obvious solution for the significant water demands of electrolysis. However, almost all commercial PM electrolysers, which we need to use because we don't need to use, but we often choose to use because they can accommodate the variable electricity output from offshore wind generation, which we know is not consistent and it fluctuates massively. But these require water that have a dissolved salt content of less than 10 parts per million. Now, for context, the salinity of offshore water of the North Sea range from 3.4 to 3.5% dissolved solids. And that's on top of microorganisms and pollution-based content like microplastics or trace heavy metals. So the level of purity we need differs massively from the salt water we're able to obtain. So it doesn't mean we can't use it, but it just means that the degree of pre-treatment required, it's essential and it's very energy intensive. So it has high associated electricity costs and ongoing operational costs. So if we're able to reduce these pre-treatment requirements even a little, it could massively help decrease those associated costs, and that would help decrease the overall kind of cost of generating green hydrogen from seawater And obviously that's the aim, to make hydrogen as accessible and attractive a proposition as possible. So we therefore want to determine the extent to which our conditions can deviate from ideal without compromising either the rate at which hydrogen is produced or the ability of the electrolyzer to continue producing hydrogen for a given period of time. So we're doing this by testing the effect of incrementally increasing total dissolved solid content. So we're talking really, really small increments, so 0.01 per milli increments, so parts per thousand, that is, on the production rate. So testing the effect on production, and then also analysing the surfaces of the membranes used to assess the extent of degradation. So it's all well and good being able to maintain a similar rate of production, but if those membranes have to be replaced twice as often, given that they're also quite a big cost and an ongoing cost for electrolyzers, that would defeat the point. So we basically want to find that sweet spot where we are able to reduce desalination requirements, but also not incur kind of greater costs due to increased level of impurities. So yeah, that's work that's ongoing at the moment that we're just kind of getting stuck into. But yeah, thank you all for listening. I apologize only because I had 15 minutes kind of rushing through things, but if you have any questions that don't get answered today, my email's on the slide, and I'd be very happy to kind of discuss anything in more detail.
Great. Thank you, Anna, for your great presentation. It was lovely to know more about how you guys are integrating all this information together. It was very nice. And well, now, dear audience, we will be opening our Q&A panel. So our panel is the opportunity for anyone to ask questions to our speakers, either about their research work or career path. So, you know, you can ask about how their daily routines look like, what they like about their jobs, or about science in general. And so, yeah, one of the aims of the webinar is to facilitate access to information about possible future career paths to our PhD students. So don't be shy to ask about career questions as well. You can type any questions you have on the chat, or if you want to speak with our speakers aloud, just raise your hand, open your mic, we can have a conversation as well. So yeah, so Q&A is open. And we do have a question already in the chat, so let's start with that, and then we can move on. So the question was, with this huge storage capacity vis-a-vis the risk involved, please, in which form do you recommend such storage, in gaseous form or compressed form, and at which temperature?
Was this being directed to me?
Yeah, it was typed during your presentation, so I believe so, yeah.
So we're looking at, so in depleted reservoir storage, we're generally talking about compressed gas storage. The correlation between depth and the volumetric density of hydrogen is like a strong positive correlation. So the deeper the reservoir, we can store basically more energy as hydrogen per unit volume. So reservoir depth is really important, but yeah, we're considering it is a compressed gas. In terms of safety, we've been storing compressed gas in depleted fields for decades. So in terms of safety concerns, it's more about making sure that when we're repurposing different things, whether we actually just need to kind of replace, especially wellheads and valves, that's a key issue in terms of safety. But I think in general, one of the perception of hydrogen as a very dangerous alternative is slightly, it's not wrong, but it's a lot more manageable than I think people anticipate. We currently in our houses have a highly flammable, highly explosive gas that we have no issue using. We have no issue turning on our oven, turning on our heating. So like, I appreciate it. I think it's the change that's more scary than the gas itself. But yes, we are, in terms of risks, there are not any kind of big anticipated risks for safety. The only risk for, not the only risk, but like the biggest risk at the moment for storing hydrogen in depleted reservoirs is the microbial environment. It's the losses. So it's not about any kind of, like, as I say, no safety aspect. It's just how much of that hydrogen are you going to lose to microbial interactions.
Lovely. Right, so we have Dr. Van der Land from Newcastle Uni. He has had his hands up, so he has a question. So if you can open your mind, please. And yeah, speak your question.
Thank you, Anna. Hi, Anna. You already followed the end of your answer to the previous question was already, that's basically part of the research we're doing in our geoscience group here at Newcastle. We got a few PhD projects on basically that microbial risk. I'd already seen your paper with Catriona, so that's good. Are you so slightly different question, more related to career? Are you in a CTD kind of project, or do you have a standalone PhD project?
It's a standalone PhD project.
Okay.
Yeah. Almost unfortunately, because it means I don't benefit from the kind of collaborations that you do get.
And I know you're already in your second year, but we do have one of our PhD students was not part of a CTD. We basically asked the CTD, like, can this PhD student join some of the things, and the answer is usually yes, because
thank you.
It's a bit of a, sometimes they have CTD things because you do a lot of like workshops. Your first year is basically half workshops and there's no time for your research, but that's a common complaint from PhD students. I was just wondering, because I know this topic a little bit, but since the Zurich is not very well known for having either offshore or a lot of oil and gas reservoirs or wind energy, what's the interest from ETH in this?
It's the modelling side.
Right,
so they have it's the energy system, and it's the chair of the energy system analysis that I'm working with. There, it was actually my supervisor at Aberdeen moved to head up that and head up a chair at PSI, the Paul Scherrer Institute as well. So I'm working in their energy system analysis group for the model development, rather than the hydrogen side of it.
So really large scale. Yeah, you got an interesting career path there from Durham, and then the Edinburgh group, and now in Aberdeen. In terms of microbial risk, is that something you also want to model later on? And do you know what kind of input things you need for that?
So it's something I would love to incorporate in the model. I think my biggest limitation is going to be time as to how much we can build into it. So at the very beginning, we're considering it like from quite a high level. So generalized assumptions about kind of temperature thresholds, that kind of thing. But if I did have the opportunity to build in a microbial risk, that would definitely be it, because I think it's one thing that would kind of wipe out lots of fields kind of from the off. So
I think that high level, there's already work there. I think Nicholas in Edinburgh and then Nicole Dopfel in Norway, they're already working on those things as well. But in the end, the more detailed you look, it probably gets more complicated. I think we're coming from the other side, where we're doing the lab work and understanding those basic processes. But that's only useful if you understand what kind of questions are coming from that high level model to put it in. So I'm trying to connect those things up. I'm just a poor geoscientist who's trying to understand microbiology, which is
I don't envy you.
we do have some expert in our group here. Good. Very interesting talk. I'm sure your email address is somewhere on here. I'll do a follow up.
That'd be great. Thank you.
Lovely. So we do have one more question for our audience in our chat. So I'll be reading it out loud. So considering the odorless and high flammability nature of hydrogen gas, how do you detect its leakage from any of the storage sites? Yeah. So that question is open. Anna or Dr. Oko, any of them, or both of you, can chat. So what do you guys think about that?
I can just jump in quickly and say that natural gas is a colorless, odorless gas. When we see it in our houses, it's had an odor added to it and a color. So we see like a blue flame on a hob, but in storage, it is a colorless, odorless gas. So we'll essentially attack the problem in the same way we currently deal with natural gas, and as I said, have done for decades. So in terms of, I think that's why this side is considered slightly less high risk than people imagine, because all the frameworks that we'll need to use kind of have already been developed. So in terms of detecting leakage, it will be monitored in a very similar way to current natural gas storage sites. I don't know if Dr. Oko has anything to add to that.
Yeah. Dr. Oko, do you have any comments on that? Or
no, not really. I think the point is in terms of detection, like in natural gases, there's a standard protocol for, a certain component to be added into it that will help detect when there is a leak or not. And this is detection in terms of like human kind of detection. In the industry, there are still going to be sensors that will be able to, that don't need odor to be able to pick leakage. There are still sensors. I think when it comes to whether you can perceive the odor or not, it's just human detection. Okay, and that works very well in domestic applications. In the industry, there be like specialized sensors that will be able to measure hydrogen composition in the ambient, from time to time. And whenever there is a spike in the hydrogen level, they can correlate that with leakage. Yeah.
Thank you.
I was just going to add something to that completely, as you say, in industry using like actually kind of sensor technology rather than purely based on human detection. There's a lot of work going on at the moment about using seismic surveying to try and detect the hydrogen gas, what's it called, the hydrogen gas contact within reservoirs, and being able to track it to make sure that the hydrogen stays sequestered within that trap, beneath that cap rock. So I know that seismic as well is something that is looking at being used as one of those kind of detection things for large scale storage, at least.
Right. I see some hands up in our audience. Mohammed, do you like to ask a question out loud?
Yes, this might be the last one I'm gonna ask.
Oh, that's
yes.
lovely. The
yes, I am
conversation
more
is the
concerned with the safety of the storage and of the use of the hydrogen gas. So with respect to the storage or the leakage question I asked earlier, I am wondering, is it possible to blend it with hydrogen sulfide so that once there is any leakage, the hydrogen sulfide odor will just make an indication that there is a leakage in the environment, and the necessary measure to curtail the leakage will just be taken by that odor from the hydrogen sulfide. So the question is hydrogen sulfide going to affect the flammability or any other property of the hydrogen if added?
Are you done?
Yes, I'm done.
Yeah, even if that was going to be possible, I will be more concerned about the environmental implication of having hydrogen sulfide and risk. Remember that in natural gas, companies spend a lot of money to take out hydrogen sulfide from the natural gas. Why would you want to put hydrogen sulfide of all gases, into it again? That's very dangerous to the environment. As I've mentioned to you, in the industry, there are odometers that can pick, because the issue of being able to smell and know when it is released, I said, is mostly in domestic applications. In the industry, there are established and well-calibrated odometers that can pick that, that can pick it better than humans will pick it. The only difference with household applications is that you don't have such odometers, for instance, fitted in your homes, all right? And that such meters may bring in, will I say, complicate things, so to speak, rather than just being able to perceive it. And then the materials that you can use to blend in with the gas, with natural gas, for instance, to be able to perceive it. I worked in a natural gas plant, for instance, for a very long time. And there is nothing like, because this is a case of, the natural gas has no smell as far as I can remember. you know. So it's not like it gets blended with some other stuff everywhere, you know. So if it is going to be blended with some components to help you perceive it, then there are established materials that are used to do that, not hydrogen sulfide.
Thank you very much, Dr. Eni. In your own case, it was a hydrogen with a carrier, which is ammonia. Ammonia
Yes.
itself is a protection and is a detection strategy, apart from being a carrier. That's why I'm not so much bothered about your strategy.
Yeah, but the ammonia, but even if you are transporting it in the form of ammonia, at some point you are still going to convert it to hydrogen.
Yes, at the point of use. At the point of use, that is understood. Yes, and this
maybe not just at the point of use alone. Okay. There could also be cases where there is a short distance kind of transport. So, for instance, if you have an industrial park here, let me say something like where you have all this industrial hub, like the Humber region, like the Teesside, you know, where you have lots of companies. So you may want to have one central tracking system in place, and then you still have pipe work that will be taking hydrogen from that point to the various end users in that place. So short distance transport, you will still be needing to transport hydrogen and not, and then in filling stations, you still need to store hydrogen. Although some people are proposing having some on-demand kind of tracking system in place in filling stations, you know.
Okay, thank you very much. I think the time is over. Thank you to both of you. The presentations have been wonderful. We're highly grateful.
Thank you.
Thank you.
Thank you.
Yeah, just if I would just add this question on public perception. Yeah, there's a lot of concern. I can't remember the community somewhere in England where they are supposed to do some testing for domestic use of hydrogen. And
I think there might be Fife in Scotland.
Yeah, and the public is actually, people are absolutely crying. I recall reading a story where a lady said they are using us as guinea pigs, kind of, for lab experiments. So people are absolutely worried about this. But you know, it's just like when will I say CO2 capture and transport was really booming around 10 years ago. I remember I had a project we're doing with National Grid in Humber area. And a big part of that project was actually engaging with the public. You know, so engaging with the public and trying to make them understand what is all the risk possible and being put in place to mitigate the risk. I think if we can get to that point, and I believe as far as hydrogen is concerned, there are folks in the social sciences that their projects are around things like this. So if we have more research-driven kind of ways of engaging with the public and letting them know all the solutions that are being put in place to mitigate any potential risk or hazard, I'm sure that people will be fine. Okay? But until that is done, acceptance is a big deal.
Yeah, well, I think that is a great high note to end our webinar today. Definitely, I couldn't agree more. I'm not in the hydrogen field, but from the energy perspective, energy literacy, right? Like telling people what is going on and why we should care, and, you know, what are the risks, what are the benefits. It's one of the most important parts, so everyone can be on the same boat together. Yeah, that's the only way to move forward. So yeah, lovely that we end in such a high note. So yeah, I'd like to thank everyone for coming today. Again, especially our speakers. With that, we finish our webinar today. It was wonderful to have everyone here. I'd like to thank Rhiannon as well from the Newcastle University Centre for Energy for helping curating or organizing our webinar series. So our next scheduled webinar is going to be the Fusion Energy webinar that will count with people from the UK Atomic Energy Authority. So don't miss that. It will be on the 5th of April from midday to 1. And so, yeah, so follow us on social media or get in touch with us via email if you want to register for that as well. Bring all your friends, everyone is welcome. And we'll be scheduling more webinars in the future. We'll be planning one per month. So maybe we'll do other energies, or we will do hydrogen again. So more discussions are coming up. So thank you everyone for coming and keep in touch to each other. It was a lovely discussion today. Lovely to have you all here. So lovely. I think it was my favorite webinar so far. So thank you so much for everyone. Have a lovely Wednesday.
Thank you for inviting me.
Thank you.
Bye.
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 Bye, guys. All the best.